theorem for board syllabus. Let f from x to y and g from y to z be two invertible functions. Then show that g circle f is also invertible function, and hence show that g circle f whole inverse equal to f inverse circle g inverse. This is one important theorem for board syllabus. Here first we must so I used to recall once again the definition of invertible functions. F from capital X to capital Y and G from Y to Z. I said in second definition, be the two functions so that f circle G equal to, so last letter G, go to G. What is its domain? Y. Just you write like that. So that f circle G equal to Iy and G circle f equal to last letter f domain X. So write Ix. This is the easy remembrance for f circle G equal to Iy, G circle f equal to Ix. So therefore under these two conditions then only f inverse equal to G. So this is the definition of inverse function. Okay. Next, another formula is there. H, G, G, F are any three functions. Then H circle, G circle, F can be written as H circle, G circle, F. Actually, in matrices, we wrote AB into C is equal to A into BC. It is called associative law. Associative law with respect to multiplication, just like that. With respect to composition, it is called associative law. Associative law means just we are changing the bracket, that's all. Changing the bracket. This bracket can be changed as like that. That's all. It is called associative law with respect to the composition. Okay. Next, next you come here. Actually, suppose this is a, say, capital F. Means what? LHS is F inverse. That is equal to, say, this total G. Then F inverse equal to G. We have to show like that. Whereas capital F equal to G circle F. Capital G is equal to F inverse circle G inverse. Okay. You come here. If F from X to Y and G from Y to Z, so that these two conditions are satisfied, then we say that F inverse equal to G. Compare this with capital F inverse equal to capital G. Then we have to show that F circle G equal to Iy, G circle F equal to Ix. Understand? Right. So first condition, F. F means what? F means this one. Let us consider F circle G. F circle G F circle G is equal to 1 minute. Actually, we have this simple formula. H circle G circle F equal to H circle G circle F. Means we can change the bracket like that. So let it be H. This will be G. This will be F. So it can be written as H circle G circle F. So H circle G, H circle G, bracket close, put in the separate bracket. Later circle G inverse, H circle G circle F equal to H circle G circle F, like that. So just I change this bracket as like that. Okay. So that is equal to bracket. Again same formula. We are using same formula. So just I am changing this bracket. Okay. You write the same circle G inverse like that. Here 1, 2, 3 functions are there just like that. So it can be G circle of F circle F inverse. Okay, I changed the bracket. That is equal to, again bracket, G circle. Now what is F circle F inverse? You come here. F circle F inverse. F is what? X to Y. F is what? X to Y. And F inverse is what? F inverse Y to X. Or we can write here Y to X. Now F inverse, it is Y to X. It is F inverse Y to X. Next, F is what? X to Y. X to Y. It is what? F. So cyclic order. Just like that. So therefore F circle, already I said this cyclic order in the definition of composition of F and G, composition of G and F. You refer it. After that you read it. Is capital Y to capital Y. Therefore simply F circle F inverse equal to I Y. So therefore it can be I Y circle G inverse. Did you understand? IY means nothing but I, identity function. So that is equal to G circle I. Just you read here I, G circle I. In matrices I into capital A equal to capital A, same matrix. I into any matrix equal to itself. In the same sense, G circle I equal to G, same function. So this total bracket gives G circle G inverse, circle G inverse. Now what is the value of our function G circle G inverse? You come here, rough work. G is what? G Y to Z, G inverse Z to Y, Z to Y. So G inverse is what? Z to Y. Next G is what? Y to Z. This is G. Next composition. It is in anti-clockwise direction. Just like that. So G circle G inverse is Z to Z. So simply G circle G inverse equal to I Z. So this is capital I Z. Therefore G circle F circle F inverse circle G inverse equal to I Z. I Z. Let it be equation number 1 of statement number 1. You come here. In this definition, what I said, last letter is what? G. Go to G function. What is its domain? Y. That's why we are getting Y. What is the last letter? G inverse. G is what? Y to Z. G inverse means what? Z to Y. What is its domain? Z. We got the same Z. We got in the same sense. So therefore, and similarly, F inverse circle means reverse order, just like that. Similarly, we are writing this result. We proved this. Similarly, we are going to write this one, this statement or this result. So, second one, circle, G circle F equal to, what I said, what is the last letter? F. F, its domain is X, that is I, X, let it be number 2. So, in the same sense, by using this one, by using for G inverse G like that, we are getting Ix. So, in the examination, directly we can write like that. So, therefore, you see there, F circle G like that. F circle G equal to something, G circle F equal to something. Therefore, from 1 and 2, therefore, from 1 and 2, from 1 and 2, G circle F is also invertible. Means what? G circle F also having its own inverse. It is the complete meaning. Invertible. And G circle F whole inverse means just like that. F inverse equal to G. F inverse equal to G. G means F inverse circle G inverse. So in examination hall, you need not to prove for the second statement. You can write directly, similarly, so and so. Understand? This is the important theorem for board level. Okay. Let f from capital X to capital Y be invertible function, then it is unique. So you can take any function. For example, f is any function, then it has a unique inverse. We have to prove like that. Okay, once again, let us recall the definition of inverse function. Let f from capital X to capital Y be the function, and if there exists another function g y to capital X, so that f circle g is equal to I y and g circle f equal to I x, then the inverse of f is g, and f and g are invertible function, mutually invertible functions. Okay, equal to g or f comma g are mutually invertible functions. Okay, you come here. F from x to y be invertible function. Already I said one definition. What is that? Only for bijective functions only it has the inverse. So here f is inverse means definitely f is a bijective function. F is a bijective function. F is bijective function means what? F is 1 1 and onto function. Onto function. Remember, 1, 1, right? Next, actually, we have to show that f will have unique inverse. We have to show like that. F will have unique inverse. For which first we assume that f will have two inverse functions. We shall take like that. Later we show you that that two functions are same. Thus are hence the theorem. Right, okay. Let g1 comma g2 according to definition. If there exists g from y to x, that's why I took g1, g2. g2 be the inverses of f. We assume like that. Okay. Then we have first condition. F circle g equal to iy means f circle with respect to g1. F circle g1 equal to iy and f circle g2 is iy. Next, second condition, g circle g1 circle f equal to ix and g2 circle f is also ix according to this condition or definition. Okay. Therefore it is what iy. It is what iy. Therefore, for example, let it be number 1. This one, let it be number 2 equation. Therefore, from 1 and 2, we see that f circle g1 is equal to f circle g2. F circle g2. What does it mean? Complete meaning. F circle g1 of y, because iy, that is equal to f circle g2 of y. So it can be written as f of g1 of y equal to f of g2 of y. So that implies, you come here, if f from a to b is 1 function, what we said there, let x1 comma x2, that is belongs to domain f of x1 is equals to f of x2, that implies x1 equal to x2. It is called 1 function, or if this condition is satisfied, then f is said to be 1 function. What is happening? F of x1 equal to f of x2 means this side no f letter. The letter f, there is no the letter f like that. Remember like that. But don't strike out like that. It is a wrong notation. You feel f is not there. Only we are writing x1, x2 just like that. If f is 1 function. So here already f is a bijective function. F is 1 and onto function. So since f is 1 function, we can write without the letter f, g1 y equal to g2 y, because f is 1 function. That's why I delete this letter f. So remaining. So clearly, therefore g1 equal to g2. What we assumed, g1 comma g2 are the inverse functions of or inverses of f. So f is 1 function. Its inverse is g1 and g2. Ultimately, this g1 is equal to g2. We proved like that. Therefore, this function f will have only one inverse. So therefore f has unique inverse, hence the theorem is useful for 2 marks question. So f from x to y be invertible function. Given that f from capital X to capital Y be invertible function. Mind it, if f is invertible function means it is bijective function. Bijective means what? It is one function and onto function. Okay. So then we can write it as f of x, small x means small x belongs to capital X, that is equal to y, comma, x belongs to capital X, small y belongs to capital Y. We can write like that according to definition. Next, it's inverse, and f from capital X to capital Y means what is f inverse, or what about f inverse? Just reverse order, capital Y to capital X means x is domain of f, then x is codomain of f inverse, y is codomain of f, y is domain of f inverse, just like that. What does it mean? That is f inverse y, small y equals to, we can write like that according to definitions. Okay, so f from capital X to capital Y. So f inverse is what? Y to capital X. Again whole inverse, such that again reverse, capital X to capital Y. So that implies like that, f inverse whole inverse of x equal to y, x equal to y. Okay, what is y? Y equal to again f of x, that is equal to f of x. It is f inverse of whole inverse of x. So therefore f inverse of whole inverse of x equal to f of x. So therefore that implies f inverse whole inverse equal to simply f. Hence the theorem. Then whether the following functions have the inverse or not. So first question, in the first question f domain, say capital A, it is capital B, 1, 2, 3, 4. This is capital B given as singleton set 10, and mapping is given 1 to 10, 2 to 10, 3 to 10, 4 to 10. 1 to 110, 1 is mapped with the 10, 2 is also mapped with the 10, 3 with the 10, 4 with the 10. So clearly it is a many to one function. Of course it is a constant function. Already I said the definition of the constant function in 11th standard. Okay, it is so f is defined from capital A to B. So therefore f from capital A to B is not one function. It is not one function. So only bijective functions having the inverse of functions. Bijective means 1 and onto, but 1 is fail. Therefore f is not bijective. So therefore that is imply f is not a bijective function. F is not bijective function. Therefore f inverse does not exist. This is the reason. Next, first one over. Next, second one. G. This is the domain, codomain. Say capital C, D. capital C, 5, 6, 7, 8, 1, 2, 3, 4, 1, 2, 3, 4, D, domain. Mapping 5, 4, 5 is mapped with 4, 6 is mapped with 3, 6 is mapped with 3, 7 is mapped with 4, 7 is mapped with 4. You see here 5, 7, both the different elements are mapped with only one element. Next 8, 2, 8 is mapped with 2. Here f of g, I mean it is given as g, the function is z. So g of 5 is equal to g of 5 equal to g of 7, g of 7. Therefore different elements will have same image. So therefore g is not 1 function. Therefore g is not bijective function. Therefore g inverse does not exist. Okay. Next, second over, third one. Here, number 3, H. Suppose E, capital F, domain and codomain, capital E, 2, 3, 4, 5, 2, 3, 4, 5, capital F, 7, 9, 11, 7, 9, 11, 13. Mapping E to F is H function. 2, 7, 2 is mapped with 7, 3 is mapped with 9, 4, 11, 4 with 11, 5 is 13. So 2 is mapped with 7, 3 is mapped with 9, 4 is mapped with 11, 5 is mapped with 13. So clearly H for different elements are mapped with different elements. Therefore clearly H is 1 1. Next E, second set, 7, it is the image. For this 7 it will have at least one pre-image in capital E. So how many pre-images are there for 7? 1, at least one is there. Okay. 9, this is the image of 3, means it has at least one pre-image in capital E. Yes. Next 11, it is the image of 4. So this it will have at least one pre-image in first set. Similarly, it will have at least one pre-image in first set. Therefore, each and every element will have at least one pre-image in the first set, capital E. Therefore, it is also onto function. Thus, it is 1 and onto function. Therefore, H is bijective function. Therefore, H inverse exists. And H inverse is equal to the set of H is given as 2, 7, 3, 9, 4, 11, 5, 13. So H inverse is equal to reverse 7, 2, 9, 3, 11, 4. We must write in reverse order. AB, if A comma B is here, we must write here B comma A, just like that. H AB, H inverse B A, just like that. 2, 7, 7, 2, 3, 9, 9, 3, 4, 11, 11, 4, 5, 13, 13, 5, 13, 5. So this is H inverse, hence the problem.